Good afternoon, our dear students, and welcome to this hour's discussion. Today, we will be looking at a concept in regression analysis called least square method. We have already had a class on regression analysis, which we tagged on YouTube as Introduction to Regression Analysis. And in that class, we explained or we mentioned that there are various approaches which one can explore when one wants to estimate the parameters of a regression equation or regression line. And of course, these methods which we discussed in our previous class are: number one, we have the maximum likelihood estimator. Maximum likelihood estimation method. Number two, we have what we call the Bayesian estimation method. The Bayesian estimation method. Bayesian estimation method. We have number three called the least absolute deviation method. Least absolute deviation method. We equally have what we call the least squared method. Least squared error method. The least squared error method. And our discussion this afternoon will be centered on the least squared error method, which of course is called least square method. Of course, when you come to this least square method, they are classified into two. Number one, we have what we call ordinary least square method, OLS. We have number one, under this least squared error method, we have number one called ordinary least squared method. And then we have what we call number two, non-linear least squared method. Non-linear least squared method. Non-linear least squared method. Equally, our discussion this afternoon will be narrowed down to the ordinary least square method, which is generally described as OLS. So anytime you see OLS in a discussion of regression analysis, then concern is made on ordinary least square method or about ordinary least square method. And of course, when we are talking about ordinary least square method now, we are concerned in a linear regression or in a linear relationship on x and y, where x is the independent and then y is the dependent. So OLS is concerned with a linear regression. And that's where our discussion this afternoon is going to be centered. So you are going to permit me to clean this board while we make a diagram of a linear regression and then be able now to explore in detail the least squared error method. So we are talking about the OLS. Talking about the what? OLS. Ordinary least square method. And then let us assume that we have a scatter diagram of the true values of x and y. So you have a graph or you have a diagram that looks this way. You have a diagram that looks this way. Here is your what? Your y. Here is your what? Your x. And here is the 0. So you might have a plot this way of the values of x and y. You might have a plot this way. You might have a plot this way and this way. So of course, our concern here now is to fit a regression equation or line using the least square method. The least square method approach is concerned with a way of fitting a regression curve or a regression line on a data set such that the sum of the squared deviation from that line is least or is minimum compared to other lines. For instance, if this is a regression line, if this is a regression line, if this is a regression line, this is a regression line, okay? This is a regression line which we have established using a method called ordinary least square method. Is what we call best line of fit. It is called what? Best line of fit. Best line of fit is called best line of fit. And of course, it is called best line of fit because when we consider the deviations of the data points from this regression line, it is going to give us what? A very minimal value. And when we talk about deviation, we are talking about the vertical distance from this data point to this line, 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 from this data point to this line. So this from here to here is what we call a deviation of a data point from the regression line or from the predicted value. This from here to here is what we equally call the deviation. And of course, another name of this deviation is what we call the residual. What we call the what? The residual. We can equally call it the what? The error values or the error values. Okay? So we are saying that if this line which we have here is best line of fit, that when we sum the squared deviations, that is the distance from here to here squared plus the distance from here to here squared plus the distance from here to here squared plus the distance from here to here squared and distance from here to here squared, and we sum it. It is going to give us the least value when we compare it to what we are going to get when we have another line x-square that is not fit using the method of least square. That is what we are saying here. And then this line which you see here is described with an equation. And that equation is given like this. That equation is given as what? Y estimate is given as beta 0 estimate plus what? Beta estimate what? X. This y, of course, is what we call our response variable. The beta 0 estimate here is the estimate of the intercept of the regression line. That is the point at which the regression line cuts the y-axis. And then this beta here is making reference to the slope of the regression line or the regression equation. So we are now going to ask ourselves, what are now going to be the estimators for beta 0 and for beta in such a way that the square deviation of the data point from this line is going to be least or is going to be minimal when compared to other methods. It has been proven or established that the estimator of the beta 0 and then the estimator of what? Of beta making use of the least square method is given by that my beta alone, my beta cap, which of course we call the slope, is given as n summation of x, y minus summation of x, summation of y, all over what? N summation of x squared minus summation of x all raised to power 2. This is the estimator of the slope when we make use of the least square method. And then the estimator for beta 0 is going to be beta 0 cap is given as, we have what? Y bar minus, we have what? Beta cap x what bar. And do remember that y bar means the mean of the response variable y, and x bar means the mean of the independent variable x. So it means that this equation can equally be written as that this is summation of y all over n minus beta what cap summation of x all over n. So if you don't see it written in this way, you can see it written in this way. So our concern now becomes, how do we estimate this and how do we estimate this? When we are giving real observations, of course, which we are going to show in our next class, then we can easily get the product of x, y, and then be able to fit in here, get the square of what? Of the independent variable, sum it and fit here down the what? The line. These least square estimators, what are their properties? Which we tag as properties of least square methods. Properties of the least square methods. So permit me to clean here while we write the properties of the least square method. Or what we call the properties of the least square estimators. Properties of the least square estimators.